Imagine this traveller, you didn't arrive here by accident. Something in the quiet pulled you as if the cosmos itself guided you to witness what drifts now between Mars and the Sun. What if the object we call 3i Atlas isn't wandering at all but moving along a 1 in 20,000 path that brushes past 3 worlds with impossible precision? What are the odds that such a silent fragment of another star would carry an 8-1 chemical signature so exact it feels engineered rather than born of dust? A light blinked once and vanished. A whisper curled inside background radiation. And now it waits in the dark. Stay a while, traveller. Picture a quiet night in a remote observatory where the only sound is the steady hum of instruments tracing the faint breath of distant worlds. For decades, Mars has appeared to us as a still and ancient planet, a cold ember drifting through the dark. Its air is thin, its surface silent, its changes so slow they rarely trouble our measurements. Yet recently subtle shifts have begun to appear, delicate alterations in temperature, traces of unexpected chemistry, and faint signatures that suggest the planet is no longer as dormant as it once seemed. Into this quiet picture enters Atlas, an interstellar object designated 3i. Its arrival is not dramatic. It moves through space with the calm precision of something shaped by vast distances and even vaster time. To most observers, it is simply another visitor from beyond our solar system. But as scientists track its composition and trajectory details emerge that cannot be dismissed as coincidence. The ratio of carbon dioxide to water ice in its structure is unusual, 8-1, an exact mixture known to influence atmospheric processes on a world like Mars. Such numbers are on paper nothing more than chemical facts. Yet chemical facts can take on the shape of intention when they arrive at perfect cosmic timing. Measurements from orbiters and ground-based telescopes begin to align. The thin Martian atmosphere shows tiny but consistent oscillations. Dust remains suspended longer than usual. Thermal readings rise by fractions barely perceptible yet persistent. Nothing here suggests catastrophe or urgency. Instead, these observations hint at a slow and deliberate shift, the kind one might expect if a planet were being gently encouraged toward a new equilibrium. Tracing Atlas backward through space adds another layer of curiosity. Its computed path aligns with regions of the galaxy associated with ancient star populations, and in a coincidence that continues to intrigue researchers, its trajectory echoes patterns recorded by early human civilizations. These early skywatchers lacked modern instruments, yet they described celestial cycles with surprising mathematical precision. While such parallels do not constitute evidence of shared knowledge, they remind us that humanity has always looked upward, always searched for rhythm in the movements of the sky. The present-day scientific community approaches these findings with caution, focusing not on speculation, but on data. Atlas viewed strictly through the lens of physics follows a coherent orbit shaped by gravity, momentum, and time. Its chemistry is measurable, its approach can be modelled, the slight warming of Mars can be monitored and compared to historical baselines. No single observation demands extraordinary interpretation. Instead, each forms part of a subtle pattern, one that invites curiosity more than concern. Perhaps the most striking aspect of this moment is not the object itself, but our response to it. As observers, we find ourselves drawn into a reflection on how little we truly control within the cosmic environment. We can measure a world's atmosphere to exquisite precision, yet we cannot dictate the broader choreography of celestial motion. We can identify anomalies, but we cannot assume purpose behind them. In this sense, Atlas becomes less an intruder and more a reminder of our place within a much larger system, an object moving according to laws that predate life on Earth. The story unfolding between Atlas and Mars is not one of alarm, it is one of observation. Mars warms slightly and we observe. Atlas passes through the inner solar system and we trace its path. Ancient records echo familiar patterns, and we compare them not to find prophecy, but to understand how humans have always sought meaning in the stars. Nothing here requires fear. Everything here invites humility. To contemplate Mars tonight is to witness a planet undergoing changes so gentle they resemble breathing. To contemplate Atlas is to consider how rarely we have the chance to study an interstellar traveller up close. and to contemplate our own role is to accept the limits of our knowledge while still valuing the clarity our instruments provide. In the end, the universe offers no conclusions, only data, motion, and silence. It continues on its course whether we understand it or not. And perhaps that is the quiet lesson hidden. Within this moment, it is possible to observe without needing immediate answers to study, without demanding certainty, and to wonder without assuming fear. It's all right not to understand everything at once. The cosmos moves slowly. Tonight it keeps its silence, and Mars turns softly beneath it. As observations deepen, scientists begin to notice that Atlas is not merely a passive traveller, but an object whose motion contains subtle deviations, small vector adjustments that distinguish it from typical interstellar debris. These shifts are faint detectable only after careful filtering of noise and cross-comparison with long-term orbital models, yet they persist across multiple datasets. Natural objects rarely exhibit such behaviour. Comets and asteroids follow ballistic trajectories shaped by gravity and the occasional burst of sublimation. Atlas, however, displays a pattern of direction changes too consistent to attribute solely to random outgassing or observational error. Rather than leaping to extraordinary conclusions, researchers approach the anomaly with disciplined restraint. They test alternative models, unknown volatiles, asymmetric surface heating interactions with solar radiation, computational uncertainties. Each explanation fits part of the data but not all. The object seems to operate under influences we do not yet understand, but this does not necessarily imply design. It may simply reflect unfamiliar physics shaped by environments our solar system never experiences. Interstellar space contains temperatures, magnetic fields, and particulate structures unlike those in our planetary neighbourhood. An object forged in such conditions could very well behave in ways that challenge our expectations. This uncertainty guides astronomers back to a more grounded question. What happens when an interstellar visitor interacts with a world undergoing slow atmospheric change? Mars offers a unique laboratory for this inquiry. Its climate responds rapidly to small variations because its atmospheric envelope is thin and its thermal inertia low. A minor increase in carbon dioxide density can alter surface pressure. A change of tenths of a degree can influence dust mobility, ice sublimation, and atmospheric mixing. These shifts do not signal transformation in the dramatic sense. Rather, they reveal how sensitive a quiet world can be to gentle perturbations. As data sets accumulate, the patterns become clearer. Mars is not being remade, it is being nudged. The term nudging in planetary science refers to changes that do not alter a system's fundamental state, but encourage it toward a nearby equilibrium. It is the difference between forcing a climate into instability and allowing it to settle into a slightly warmer, slightly more dynamic pattern. In this context, Atlas may be acting as nothing more than a source of volatile materials, its composition releasing molecules into a planetary environment ready to respond. This interpretation aligns with what we know of cosmic evolution. Worlds are shaped gradually by impacts, by seasonal cycles, by the wandering debris of stellar nurseries. Interstellar objects have likely played roles in distributing water organics and atmosphere-altering compounds across many systems. What appears unusual to us may simply reflect the slow, interconnected processes that operate on galactic timescales. The presence of carbon dioxide and water ice on Atlas does not imply intent. It implies history, the chemical heritage of a place and time far removed from our own. The more intriguing question lies not in the object's composition, but in its timing. Atlas arrives when humanity possesses instruments sensitive enough to notice subtle atmospheric shifts on Mars, yet not powerful enough to control or meaningfully alter them. This coincidence emphasizes the limits of human agency in planetary scale processes. We can observe, measure, and model, but we cannot direct the behavior of a world, certainly not one hundreds of millions of kilometers away. The cosmos moves independently of our expectations, inviting us to participate only as observers. This perspective becomes especially relevant when considering the ancient astronomical traditions that recorded long cycles in the sky. Early civilizations tracked celestial movements with remarkable dedication, charting the progression of stars, planets, and eclipses across centuries. Their mathematical frameworks were shaped by careful observation, not by modern astrophysics, yet they often recognise periodicities that align with present-day measurements. When modern scientists compare these ancient records to today's data, they find echoes, not prophecies, but evidence of humanity's long-standing relationship with the night sky. The recurring alignment between human attention and cosmic phenomena suggests something subtle about our species. We are observers by nature. Whether through naked eye astronomy or deep space telescopes, humans seek patterns that help them understand their place in the larger structure. Atlas's arrival then is not a disruption, but an opportunity, a chance to witness how interstellar material interacts with a planetary environment in real time. What emerges from this moment is not a narrative of control, but one of humility. We cannot steer Atlas. We cannot dictate Mars's response. We can only record the unfolding data, compare it to earlier cycles, and refine our models of planetary change. This is the essence of scientific observation, a partnership between curiosity and uncertainty, grounded not in fear, but in respect for complexity. Mars will continue to shift in small, measurable ways. Atlas will complete its passage and drift back into the dark between stars. Humanity will keep collecting quiet streams of information, each data point a reminder that our understanding of the universe is always partial, always expanding, and always subject to revision. Some mysteries, as scientists often admit, are not puzzles to be solved immediately, but phenomena to be witnessed patiently, and in this case witnessing may be the most meaningful act available to us. It allows us to participate not as agents of change, but as observers of a cosmos that unfolds according to laws far greater than our brief lifetimes. It's all right not to know the full story yet. Tonight the stars continue their silent work and Mars turns gently beneath their light. As the investigation continues, scientists attempt to construct a coherent timeline linking Atlas's arrival with the observable changes on Mars. The resulting models are elegant but incomplete, intriguing sequences of cause and effect punctuated by uncertainties. Planetary science often operates at this boundary, where the available data suggests a trend, but the underlying mechanism remains opaque. In this case, the presence of additional carbon dioxide in the Martian atmosphere correlates with the object's trajectory, yet correlation alone cannot confirm causation. Researchers proceed cautiously, aware that premature conclusions risk overshadowing the delicate truth hidden in the data. Planetary atmospheres, especially thin ones like that of Mars, are sensitive to perturbations. Minor injections of volatiles can produce noticeable shifts in temperature and pressure, not because the quantities are large, but because the baseline environment is so minimal. When scientists examine Mars through spectrometers and thermal sensors, they see a planet responding to external influences with remarkable sensitivity. Whether Atlas is the source of these influences, or simply a coincidental traveller, remains an open question, but the interactions are undeniable. The changes are measurable, and measurement is the foundation upon which all scientific understanding is built. In an effort to trace the origins of Atlas, astronomers model its position backward across thousands of years, accounting for the gravitational pull of stars' gas clouds and the slow rotation of the Milky Way. These calculations place the object's point of origin in the region known as the thick disk, a part of the galaxy characterized by ancient stars formed in environments different from our own. This does not imply intention or message. It merely offers a clue about the chemical and structural history of the object, hinting that it may have formed in conditions similar to those that shaped our solar system billions of years ago. Curiously, this reconstructed trajectory resembles patterns noted by ancient sky-watching cultures. The resemblance is unlikely to indicate a shared purpose. Instead, it illustrates how human beings throughout history have observed and attempted to understand celestial cycles. The Sumerians, Egyptians, and Maya all recorded astronomical movements with a level of dedication that produced patterns still recognizable today. Their observations do not guide modern astrophysics, but they remind us that humanity has always used the sky as a reference point, seeking stability in the steady motions of planets and stars. Comparing those ancient records to current data reveals an unexpected alignment, not in prophecy, but in attention. These civilizations noticed long cycles because the sky was their primary clock. We notice them today because our instruments are capable of detecting subtle gravitational influences that they could only infer. The continuity between ancient and modern observation highlights something essential about human cognition. We construct meaning through patterns, even when the patterns emerge across vast spans of time. This recognition leads scientists to consider a broader philosophical point. The act of observation is not merely a scientific process. It is also a cultural and psychological one. Human beings have always looked upward, seeking rhythm in the movements of distant worlds. When a new object like Atlas enters our solar system, we inevitably place it within the larger narrative of cosmic history, a narrative composed of data, memory, and curiosity. The object itself does not seek interpretation, it simply exists. The interpretation arises from us. While some interpretations become elaborate, speculating about ancient knowledge or orchestrated events, scientists remain grounded in what can be measured. Atlas's composition, trajectory, and behaviour are catalogued carefully. Simulations are run, hypotheses are tested. The object follows the laws of motion altered only by the conditions it encounters. Its seeming anomalies may arise from physics we have not yet encountered firsthand, rather than from external guidance. Interstellar objects often behave differently than those born within our solar system, because they have experienced different forces and histories. As scientific teams examine the changes on Mars, the focus shifts from speculation toward verification. Mars is a dynamic planet shaped by cycles of dust frost and atmospheric loss. Any additional volatiles introduced into this delicate system could produce noticeable effects. These effects are not inherently dramatic. Instead, they resemble the early stages of a long-term climate adjustment, a subtle redistribution of energy, a modest increase in atmospheric mixing, a barely perceptible thickening of air. Such changes underscore the sensitivity of planetary environments. Even small variations can echo across entire climate systems, especially in worlds already balanced on thin margins. For Mars, which has hovered on the edge of habitability for billions of years, a slight shift in atmospheric composition may reveal latent processes otherwise invisible. The melting of a few grams of polar ice, the suspension of dust for longer intervals, or the rise of a fractional degree in surface temperature, all these can cascade quietly into broader patterns. These observations invite a deeper reflection about the nature of planetary change. Transformation in the geological sense is rarely sudden. It unfolds across eons, shaped by the cumulative effect of countless small events. Whether Atlas contributes to such events intentionally or incidentally is secondary to the larger insight the cosmos is interconnected, and worlds evolve not in isolation but through continuous exchanges of matter and energy. In this light, Atlas becomes less a singular anomaly and more a participant in the long history of material migrating across the galaxy. Ice-bearing objects, carbon-rich debris and silicate fragments have travelled between star systems since the formation of the Milky Way. Their interactions with planets, atmospheres, and magnetic fields contribute to the gradual shaping of environments. Atlas simply offers a rare opportunity to observe one such interaction in real time with modern instruments. The beauty of this moment lies in its quietness. No urgency is required to appreciate the unfolding science. The observations themselves are enough small variations in atmospheric density, subtle shifts in thermal profiles, gentle changes in dust behaviour. Together they form a picture not of interference but of natural processes responding to an unusual visitor. Human ingenuity allows us to track these changes and compare them to historical patterns. Yet our role remains observational, not interventionist. We watch Mars because watching is what we can do. The planet does not require our guidance, nor does Atlas. The cosmos adheres to its own logic, patient and precise. Our task is to understand that logic without imposing narratives of fear or control onto it. In the end, the connection between Atlas and Mars may prove subtle, indirect, or purely coincidental. But even coincidence can teach us something valuable. It reminds us that our solar system is not isolated. It is part of a larger environment shaped by the slow drift of interstellar material. To witness this interaction is to be reminded of the continuity between all cosmic phenomena, from ancient dust clouds to modern worlds, from silent visitors to attentive observers. And it is enough for now simply to observe. The cosmos continues its work quiet and undisturbed, while Mars turns gently beneath the distant sunlight. As scientists expand their investigation, they begin examining the possibility that Mars has undergone similar atmospheric episodes in the past. Geological records preserved in sediment layers and mineral deposits across the Martian surface reveal that the planet has experienced intermittent periods of warming, sporadic releases of trapped gases and occasional shifts in atmospheric density. These events are often linked to dust storms, volcanic deposits or orbital variations, and none require the presence of an external catalyst. This context helps frame the present changes not as unprecedented anomalies, but as part of a long and complex climatic history. Still, what makes the current episode compelling is that it unfolds precisely as Atlas passes through the region. Because of this coincidence, multiple research teams conduct comparative analyses overlaying present atmospheric readings with long-term climate models. The data show patterns that diverge subtly from known cycles, differences small enough to elude casual observation yet consistent enough to prompt deeper inquiry. Some scientists argue that the divergence might reflect a rare confluence of seasonal dynamics and stochastic events. Others point out that the chemical inputs associated with Atlas align unusually well with the timing of these divergences. In either case, the scientific response remains cautious, built on layered analyses rather than simplified interpretations. The physics governing these interactions remain grounded in established principles. Carbon dioxide affects surface pressure and temperature. Water vapor influences cloud formation and local humidity. The behavior of dust alters how heat is absorbed and reflected. These mechanisms operate predictably regardless of the source of the materials entering the Martian environment. The presence of those materials, however, raises questions about their origin, questions that the observational record does not yet answer fully. It is not uncommon for interstellar objects to deliver volatile compounds as they pass through planetary systems. What is uncommon is having instruments precise enough to track that delivery in real time. This opportunity motivates a broader scientific effort to model how interstellar debris influences the evolution of planetary climates. Researchers compare Mars's current shifts to studies of Earth's atmospheric interactions with comets and micrometeorites. They look at exoplanet data, searching for parallel phenomena in distant systems. These comparisons suggest that planets across the galaxy may experience occasional boosts in volatile content due to passing objects potentially contributing to long-term climate variability. While such events are rare, they represent a natural mechanism for redistributing chemical materials across stellar neighbourhoods. Within this framework, Atlas becomes an important data point rather than an outlier. Its composition and motion contribute to a larger understanding of how planetary environments are shaped by interstellar traffic. Even more importantly, its arrival occurs at a moment when humanity possesses the tools to observe that process in detail, a convergence of circumstance that carries scientific value, irrespective of interpretation. What may seem like precise timing from a narrative perspective is, from an astrophysical standpoint, an example of how observation depends as much on technological readiness as on cosmic events. This readiness extends into the study of ancient astronomical records, which have drawn renewed interest as researchers compare early sky charts with contemporary orbital reconstructions. The level of accuracy found in certain ancient documents, particularly those involving long-period cycles, continues to surprise modern analysts. However, this accuracy does not necessarily imply external instruction or hidden insight. Instead, it reflects the persistence and precision of early observers who used the sky as both calendar and compass. Human beings devoted generations to measuring celestial movements because such knowledge had direct practical applications in agriculture, ritual, and navigation. When these early records align loosely with modern orbital models, the alignment is best understood not as evidence of advanced external knowledge, but as a reminder that long-term observation naturally reveals periodicity. Over centuries, even simple tools can detect slow celestial patterns. The true marvel lies not in the implication of external influence, but in the dedication of human cultures to the patient study of the heavens, a dedication that continues today through telescopes, probes, and orbital observatories. As the conversation around Atlas's trajectory grows, scientists emphasize the importance of distinguishing between coincidental alignment and causal relationship. the fact that multiple ancient cultures recorded long astronomical cycles does not establish a link to the current object. It illustrates only that the sky has always been a source of structured information, and that civilizations separated by geography often converged on similar observations because they were watching the same predictable system. These reflections help situate Atlas within a broader context. Rather than viewing its arrival as an isolated or exceptional event, researchers see it as one chapter in a long narrative of cosmic exchange, a narrative involving drifting material, planetary responses, and human attention. The object's behaviour challenges certain expectations, but challenges in science serve as catalysts for deeper understanding, not grounds for alarm. The subtle shifts on Mars continue to unfold. Spectrometers trace the dispersion of volatiles. Thermal imagery maps delicate changes in surface heating. Dust lift models adjust, attempting to account for higher suspension rates. Each new dataset adds refinement to existing theories, not disruption. Even unexpected findings become stepping stones toward more complete climate models. In this process, scientists are reminded of the scale at which cosmic phenomena operate. Interstellar objects travel for millions of years before reaching a star system. Planetary atmospheres evolve over geological timescales punctuated by small yet cumulative influences. Human scientific inquiry spans only a few centuries in comparison, and even today's breakthroughs represent early steps in a much longer exploration. Recognizing this scale encourages a sense of proportion. Atlas may seem dramatic from the vantage point of a civilization just beginning to study the cosmos deeply, but within the universe's broader rhythms it is one movement in a continuous ancient flow. This understanding underscores a key point: observation is not a passive act. It shapes how we interpret our place in the cosmos. When we examine Atlas and Mars, we're not uncovering a hidden script. We are participating in the long human tradition of learning through attention. We refine our models, test our assumptions, and accept that knowledge emerges gradually through accumulation rather than revelation. In the quiet hours of data processing and long-term modelling, a kind of clarity emerges not about the intentions behind cosmic events, but about the nature of scientific inquiry itself. It is a pursuit that values patience over immediacy, evidence over speculation, and understanding over certainty. Atlas gives us a rare opportunity to observe complexity in motion, and Mars offers a landscape that responds to that complexity in subtle but measurable ways. The universe does not hurry, and neither must we. Our role is to observe the unfolding patterns, refine our understanding, and acknowledge that many questions remain open. The quiet interaction between Atlas and Mars continues, and for now it is enough to watch and learn as the data reveals its gentle, persistent story. As observational campaigns expand, researchers begin comparing Mars's recent atmospheric fluctuations with broader datasets gathered from Earth's own upper atmosphere. Similar perturbations, minor shifts in ionization layers, faint chemical traces at high altitudes, and temporary anomalies in magnetic field alignment have appeared intermittently over the past several years. While none of these events are severe, their timing aligns intriguingly with periods when Earth passed through regions of increased interplanetary dust, or when rare cometary debris streams intersected our orbit. In this context, the emerging data serve as a reminder that planetary environments are not isolated systems. Earth, Mars, and every other world within the solar system participate in a shared exchange of particles, radiation, and momentum. Cosmic dust drifts through the heliosphere continuously. Solar storms modulate magnetic fields on timescales of minutes to months. Tiny shifts in the distribution of charged particles ripple across planetary atmospheres in patterns that take years to interpret. Seen from this perspective, the faint changes currently observed on Earth are not unprecedented. They are part of the solar system's natural background variability, an intricate ballet of energy and motion we are still learning to read. Researchers examining these recent anomalies emphasize that small atmospheric fluctuations do not imply external intervention or coordinated design. Instead, they reflect the sensitivity of modern instruments capable of detecting variations far below the threshold of human perception. The more finely we measure the world, the more complexity we uncover, and the more we appreciate how dynamic even a stable environment can be. What once appeared uniform now reveals subtle textures, shifts of a fraction of a percent in chemical composition, faint pulses in the magnetosphere, slight redistributions of thermal energy. These signals are not unusual, they are simply newly visible, yet the convergence of events Atlas approaching Mars' atmospheric readings, diverging from baseline models, Earth showing mild but measurable anomalies, invites deeper study. This is not because the alignment suggests a specific cause, but because science advances by investigating patterns, even those that appear coincidental. When data streams intersect, they create opportunities for insight. When variables shift simultaneously, they allow researchers to test models more rigorously. The moment becomes a laboratory, not a warning. In this laboratory, scientists revisit theories of planetary, coupling the idea that changes in one planetary environment can influence another through indirect pathways. Solar radiation oscillations, fluctuations in the solar wind, and variations in heliospheric magnetic structures can propagate through space and produce effects across multiple planets. These mechanisms operate regardless of any interstellar visitor. Atlas simply happens to be present at a time when the solar system is experiencing natural variability, offering a point of reference rather than a source of disruption. This framing encourages a measured approach, avoiding assumptions while embracing curiosity. Although Atlas's trajectory exhibits characteristics that differ from previous interstellar objects, these differences do not necessitate extraordinary explanations. Small non-gravitational accelerations are well documented among comets caused by outgassing jets, uneven sublimation, and structural properties that produce asymmetric thrust. When such forces act consistently over long periods, they can create trajectories that, while unusual, remain within the realm of physical plausibility. Similarly, Mars's evolving climate states do not indicate engineered transformation. Rather, they reflect the delicate interplay between volatile inventories, dust cycles, and the thermal dynamics. If Atlas contributes any material to this process, its role is additive rather than directive, another ingredient drifting into a system already shaped by millions of years of natural processes. Discussions about ancient records often arise in parallel with these scientific investigations, and while these texts contain intriguing astronomical references, their accuracy does not imply advanced external input. Many early civilizations devoted immense effort to observing the sky not as a scientific exercise but as a means of marking seasons, predicting floods and aligning ceremonial activities. Over generations, such observations accumulate into surprisingly sophisticated patterns. Alignments with modern, orbital models, while noteworthy, are better understood as testament to human perseverance than as evidence of external design. This reinterpretation allows researchers to view ancient knowledge with respect rather than speculation. These cultures observed the same celestial motions we do today, and while their mathematical frameworks differed, their dedication to tracking cycles enabled them to construct accurate records of long-period phenomena. Their achievements highlight humanity's enduring relationship with the cosmos, a relationship built not on revelation but on patience. The present moment then becomes part of that same lineage. Modern scientists trace the path of Atlas as meticulously as ancient watchers track the progress of wandering stars. They sit in observatories surrounded by data streams, just as their predecessors stood beneath open skies, decoding faint patterns of motion. The tools have changed, but the impulse remains the same: to understand how the universe shapes the world around us, and how our place within it can be perceived through careful attention. In that spirit, researchers exploring Atlas's passage emphasize not drama, but continuity. Interstellar objects have visited the solar system before. Planetary atmospheres have shifted countless times. Magnetic fields have quivered, dust has drifted, and ancient cultures have looked upward in wonder for as long as humanity has existed. The current convergence of data points is neither a singular anomaly nor a cosmic turning point. It is another moment where observation becomes insight, and insight becomes part of the slow accumulation of scientific understanding. As the models refine, a more nuanced picture emerges. Mars is entering a phase of mild climatic variability. Earth continues to respond to natural heliophysical cycles. An Atlas gliding quietly through the solar system offers a rare chance to observe interstellar chemistry interacting with planetary environments. These processes unfold within the vast, slow rhythm of the galaxy, far larger than any single event, yet small enough that human instruments can capture their details. In accepting this view, scientists find a sense of balance. Uncertainty does not imply danger. Complexity does not imply intervention. Instead, both reflect the nature of a universe that evolves through subtle exchanges of matter and energy, shaped by physics rather than intention. Atlas passes through this system not as a messenger, but as a traveller, an object shaped by eons drifting through gravitational contours that long predate humanity. Our task is not to assign meaning, but to measure, interpret, and learn. The data gathered during this period will eventually inform new climate models, refine theories of interstellar composition, and improve understanding of solar system dynamics. Its significance lies not in mystery, but in the opportunity to transform curiosity into knowledge. In this quiet work, scientists find reassurance. The cosmos is vast but not incomprehensible. Its movements are complex but not hostile. Atlas will continue its path. Mars will continue its evolution, and Earth will continue its observations. These processes unfold without haste, inviting us to follow them with patience rather than urgency. And so the study continues slow, careful and grounded, honouring both the scale of the universe and the human desire to understand it. As data from Mars orbiters accumulate, researchers begin to notice a pattern that, while subtle, is consistent across multiple instruments. A gradual rise in the variability of localised temperature profiles near the planet's mid-latitudes. The fluctuations are small fractions of a degree, but persistent enough to draw scientific interest. Rather than pointing toward any external mechanism, these changes align well with established models of dust redistribution, seasonal CO2 sublimation, and energy imbalance driven by shifting albedo patterns. Mars has always been a world of delicate instability. Its thin atmosphere responds dramatically to minor perturbations. A slight increase in dust lofted into the air can reroute thermal currents across entire hemispheres. A marginal shift in solar incidence can deepen or weaken temperature gradients that have shaped Martian weather for millions of years. The planet breathes slowly, almost imperceptibly, but always in accordance with physics we can trace and model. As scientists analyse these changes, they note how easily human minds drift toward a narrative. An object appears, a planet fluctuates, and our instinct is to connect the two. Yet connection is not causation, and nature rarely adheres to human storytelling. The fluctuations owe their origins to cycles that began long before Atlas's arrival, cycles tied to the planet's axial tilt dust reservoirs and the quiet interplay of sunlight and surface ice. In every data set, Mars demonstrates consistency with itself. Its variations follow historical patterns, dust storm precursors, migratory frost lines, subtle recycling of volatiles between poles and atmosphere. Even if Atlas were absent, these changes would emerge as they have for decades. And so, the scientific community remains steady, embracing complexity, without leaping toward extraordinary explanations. Meanwhile, Earth-based telescopes provide improved parallax measurements of Atlas's motion. Its path through interplanetary space is peculiar, yes, but not unprecedented. Small adjustments in trajectory become comprehensible when researchers consider its structure-mass distribution and possible asymmetric sublimation. The lessons learned from objects such as one Oumuamua and a Tuam Borisov continue to inform new models revealing how heterogeneous materials can behave unexpectedly under solar heating. Atlas, like many interstellar fragments, appears to carry a mixture of volatiles locked in the uneven matrices. As sections warm unevenly, gas release produces a regular thrust, tiny but measurable, across millions of kilometers. The object's path becomes a record of these microevents, each jet or release leaving a faint signature in its journey. When viewed through this lens, Atlas no longer seems like an anomaly. It becomes a traveller shaped by natural processes obeying physical laws without deviation. The scientific response to these observations is not alarm but curiosity. This is the first time humanity has instruments capable of monitoring an interstellar object with such fidelity. Every fluctuation in brightness, every motion in its trajectory, Every spectral signature is a window into material histories that began beyond our sun's influence. Atlas carries with it the imprint of distant stars' environments we cannot visit, and timescales we rarely contemplate. Its very presence expands the boundaries of what humanity can study, yet even these insights are tempered by the humility intrinsic to modern scientific practice. No matter how detailed the measurements become, limitations persist. Instruments drift, data accumulate unevenly, and cosmic dust interferes with readings. Researchers must lay a caution atop curiosity, recognizing where conclusions give way to speculation. The unknown is not a void to fill hastily, but a space to respect. Historical reflections often enter these discussions, particularly when journalists or the public draw parallels to ancient observations. Civilizations across the world recorded celestial events with striking accuracy for their time, and some correlations between modern data and ancient records are indeed remarkable. But scientists are careful to frame these parallels properly. Human cultures have always engaged deeply with the sky. Patterns that seem uncanny often arise from the sheer volume of historical data combined with the natural human tendency to search for significance. Ancient astronomical achievements deserve admiration, not because they predict modern discoveries, but because they demonstrate how across time humanity has continuously turned upward in search of understanding. Those early records etched on clay tablets carved into stone aligned with monuments represent the first steps in a lineage that extends directly to the data streams flowing through today's observatories. Modern researchers stand on that continuum. They calibrate sensors correct for noise-compare models and speak cautiously of confidence intervals and statistical weight. In this measured work, they find stability. The scientific method offers grounding where speculation might otherwise grow wild. Every question becomes a reminder of how understanding is built. One observation at a time, never rushed by narrative. Even the idea of interstellar coordination, a concept often mentioned in public discourse, offers more philosophical reflection than scientific implication. The universe is vast enough for coincidence, and human history is long enough for patterns to emerge that evoke wonder without requiring external orchestration. Alignment does not necessitate design. Sometimes it is simply the product of long-term natural cycles intersecting with human attention. What Atlas ultimately provides is an opportunity to study the galaxy's debris with unprecedented clarity. If its trajectory intersects with Mars's orbital space, the interaction becomes a scientific gift, an experiment conducted not by intention, but by cosmic circumstance. Researchers will examine whether its materials disperse, whether its dust seeds new chemical reactions, or whether its passage leaves no detectable trace at all. All outcomes hold value because each one adds to the growing mosaic of knowledge about how interstellar objects behave in planetary environments. Against this backdrop, the convergence of Mars's natural variability and Atlas's passage becomes less a mystery and more a moment of scientific resonance. Two independent phenomena emerging simultaneously create an environment rich with insight but not with threat. The work is patient, the pace deliberate, and the interpretations cautious. The cosmos, vast and ancient, invites observation rather than urgency. In the end, the most significant development during Atlas's journey may be the refinement of human understanding, new models, new questions, new appreciation for the subtleties of interplanetary physics. Mars breathes, Atlas drifts, and Earth observes. Each plays a role in a story not of intervention but of interconnectedness. The solar system is a dynamic living environment shaped by forces both familiar and faint, and humanity is only beginning to perceive its full complexity. The object continues on its course, neither hurried nor purposeful, carrying with it the quiet history of distant stars. Mars continues its eternal cycles, whispering its thin winds across rust-red plains, and Earth continues to watch, measure, and learn, standing as one more participant in a universe that unfolds according to laws older than memory. As the months progress, the observational focus begins to shift from isolated measurements to broader system-wide relationships. Scientists merge datasets from orbiters, ground telescopes, ionospheric monitors, and solar observatories to form a more cohesive picture of the current heliophysical environment. When stitched together, the data reveal a solar system in gentle motion magnetic fields tightening and relaxing dust streams, redistributing and subtle atmospheric patterns emerging in ways that align with long-established cyclic behaviours. Rather than portraying a universe reacting to a single event, the combined data illustrates something more reassuring, that the solar system operates through layered rhythms, each unfolding across its own timescale. Some cycles span months, others stretch across decades or millennia. These temporal patterns overlap, creating complex signatures that are easy to misinterpret when viewed in isolation, but become comprehensible when placed within the larger context of solar dynamics. Atlas's presence intersects with these rhythms but does not dictate them. It is one more participant in a system governed by gravity radiation pressure and the quiet, persistent flow of interplanetary particles. The data show how its dust interacts with sunlight, how ionized fragments respond to solar wind streams, and how its surface warms unevenly as it approaches perihelion. Nothing in these interactions violates known physics. Instead, they extend our understanding of how interstellar materials behave when placed within our local stellar environment. This understanding grows deeper when researchers examine the object's composition with refined spectral analysis. The signatures reveal volatiles consistent with other interstellar objects, frozen carbon dioxide trace hydrocarbons, faint water remnants locked within mineral matrices. These components suggest a long journey through cold interstellar space shaped by time and exposure rather than any engineered intention. Its structural heterogeneity creates the very forces that redirect it subtly as it moves. The trajectory bends not because of design, but because of physics quietly expressing itself across millions of kilometers. In laboratories, the study of these materials provokes new questions about chemical pathways in interstellar environments. What reactions unfold within molecular clouds? How do cosmic rays alter the structure of frozen compounds over centuries? What roles do these fragments play when they enter young planetary systems? Each question opens avenues for research, extending far beyond the specifics of Atlas's passage. Meanwhile, Mars continues its own cycles, largely unaffected by the interstellar visitor. Subtle changes in pressure gradients match seasonal expectations. Dust levels rise and fall in accordance with past observational records. Even variations in reflectivity across polar regions echo patterns documented by early spacecraft missions decades ago. When researchers overlay this year's data atop previous cycles, the similarities become more striking than the differences. This consistency reminds scientists of a central principle. Planets are dynamic systems shaped by countless overlapping influences. A slight shift in solar energy distribution can produce temporary asymmetries. Dust storms originating from a single valley can cascade into hemisphere-wide effects. A minor atmospheric perturbation can appear significant when viewed through freshly calibrated instruments. But even these changes occur within a familiar band of variability. Mars remains Mars' restless cold and governed by its own internal logic. Parallel to the scientific work, philosophical discussions begin to surface in journals and conferences. Scholars reflect on the broader meaning of interstellar objects entering the solar system. Some see these passages as reminders of our interconnectedness with the galaxy. Others view them as opportunities to refine our understanding of cosmic evolution. A few frame them as symbols of perspective, encouraging humanity to anchor itself not in speculation but in curiosity grounded by evidence. The common thread through these discussions is humility, the recognition that the universe requires no narrative beyond what natural processes provide. Atlas does not arrive with intention, it arrives because gravity allowed it to drift. Mars does not fluctuate for a hidden purpose, it fluctuates because of energy, transferred dust transport and seasonal tilts. Ancient civilizations did not track celestial objects due to cosmic coordination. They track them because the night sky has always been humanity's oldest laboratory. In acknowledging this, scientists find themselves aligned with those early observers. The tools have changed: spectrometers instead of stone markers, orbital cameras instead of naked eyes, but the impulse remains the same. Humans look upward, not for warnings but for understanding. The cosmos offers no promises and issues no threats. It simply presents itself, and we interpret its silent patterns in the language of physics, mathematics, and observation. This recognition eases many of the anxieties projected onto Atlas's journey. The object's significance lies not in what it might cause, but in what it helps us see: the resilience of scientific inquiry, the richness of interplanetary interactions, and the enduring human desire to learn. Its passing becomes a moment of calibration, a quiet opportunity to refine models, improve instruments, and deepen our appreciation for the structures that bind the solar system together. As Atlas moves closer to the inner system, predictions suggest it will continue shedding material in small, irregular bursts. This dust will scatter through solar radiation fields, perhaps contributing faint streaks to background measurements, perhaps dissipating invisibly. If a fraction of these particles enters Mars's atmosphere, they will join the planet's natural dust cycle, indistinguishable from native grain suspended in thin winds. If they pass Earth, they may join the planet's constant influx of micrometeoroids, tens of thousands entering our atmosphere every day, most too small to ever notice. In this way, Atlas becomes part of the solar system's ongoing exchange of matter. Nothing about its presence interrupts the natural choreography. Instead, it offers an opportunity to witness the choreography more clearly, revealing how seamlessly interstellar and solar system phenomena interweave. The more scientists observe, the more the story resolves into clarity, not a disruption but a continuation, not an intervention but a passing, not an upheaval but a lesson in scale. The universe is not reacting, it is unfolding. And our role is simply to watch, to measure, and to understand that even the extraordinary becomes familiar when viewed with steady attention. Each night, telescopes continue their silent work. Photons scattered across unimaginable distances enter detectors with the same quiet persistence they always have. Computers sort data. Researchers refine their models. The rhythm of scientific progress continues unbroken, even as Atlas traces its faint arc across the sky. In this constancy, there is comfort. The cosmos does not hurry, and it does not warn. It merely reveals what it has always been, one observation at a time. As the observational season deepens, a clearer understanding emerges of how interstellar visitors integrate into the long-term rhythms of the solar system. Researchers track the ways in which Atlas's presence influences the distribution of interplanetary dust, subtle, diffuse, and entirely consistent with previous models of dust-object interactions. When sunlight strikes the small grains shed from its surface, photons transfer momentum, pushing those particles outward into faint widening spirals. These spirals contribute to the diffuse background glow often observed near the ecliptic plane known as the zodiacal light. For most observers, the zodiacal light is invisible, washed out by artificial illumination, or lost in atmospheric haze. But for astronomers working from remote deserts or high-altitude observatories, the glow forms a soft, triangular sheen rising from the horizon after sunset. It is the visible texture of the solar system's slow rotation, illuminated dust marking the gravitational pathways along which planets orbit. Atlas contributes a whisper to this glow, not a transformation, merely an addition, like a single droplet joining an ocean that has existed for billions of years. This subtlety encourages researchers to reflect on the scale of influence needed to shape planetary environments. Even Earth's atmosphere, dense, energetic, and constantly refreshed, changes slowly under external forces. The solar wind strips a small number of particles each second, but Earth's magnetic field deflects most incoming flows. Cosmic rays ionize molecules high in the stratosphere, but their aggregate effect is measured in atomic terms, not global shifts. Planetary systems evolve through persistent forces, not punctual events, and even dramatic phenomena such as asteroid impacts or volcanic eruptions operate within the framework of physics that governs slow accumulation. With this understanding, the scientific community evaluates Atlas not as an agent of change, but as a data point, another fragment offering clues about the conditions beyond the heliosphere. Spectral analyses refine insights into its origin. The ratios of isotopes suggest prolonged exposure to interstellar radiation. The mineral composition hints at environments near older stars where heavier elements formed sparingly. Each measurement narrows the possible evolutionary paths that shaped the object, providing astronomers with a tangible relic of distant cosmic processes. These findings highlight one of the most profound aspects of interstellar objects. They are messengers of natural history, not intention. Each carries the imprint of ancient stellar nurseries, supernova remnants, and molecular clouds where dust condenses into solids. Their journeys are shaped by gravitational tides, stellar winds, and the quiet drift of billions of years. When they enter planetary systems, they bring stories, not warnings in the language of chemistry and motion. Atlas's story, like many before it, reminds scientists that the galaxy is not empty, but full of wandering material shaped by environments far older than our Sun. As new analyses unfold, researchers return to the question of why interstellar objects capture the public imagination so profoundly. Part of the fascination lies in their origin. They come from elsewhere carrying the unknown. But a deeper reason scientists suggest is that these objects reveal scales of time and distance that challenge intuition. A fragment that travelled for millions of years can appear suddenly in the sky, visible for mere months before fading back into the void. Its lifespan dwarfs human history, yet we encounter it for a fleeting moment. This juxtaposition of immensity and brevity encourages a certain philosophical quiet. Scientists speak of how observing Atlas alters their sense of time. Instruments track changes on hourly or daily intervals, but the object's trajectory reflects forces acting over epochs. Each position measurement is a collaboration between human precision and cosmic patience. In these moments, researchers find a strange comfort, the understanding that human life, though brief, can reach toward phenomena shaped across unimaginable spans. The idea extends naturally into studies of Mars. The planet's cycles, dust storms, frost migration, polar cap fluctuations repeat on seasonal and multi-year timescales. These processes are steady, gradual, and governed by energy balance rather than external intervention. When placed alongside the immense age of interstellar objects, Mars's rhythms appear almost familiar, like the breath of a planet living by its own internal clock. The changes currently observed, minor and expected, become part of this quiet continuity. Conversations among scientists increasingly emphasize that the search for meaning should not overshadow the pursuit of understanding. The cosmos offers intricacy without the need for intention. The alignment of events, Atlas's passage, Mars's atmospheric variations, and Earth's high altitude fluctuations can be interesting, without implying a singular cause. In complex systems, coincidences arise naturally, and it is the responsibility of the scientific method to discern correlation from significance. Yet the questions themselves remain valuable. Asking why coincidences occur pushes researchers to refine models, improve instruments, and identify where assumptions need re-evaluation. Curiosity becomes a tool, not a conclusion. Even mistaken hypotheses lead to better understanding, as they force scientists to delineate what is possible from what is merely plausible. Atlas, by its presence, inspires these questions not through mystery but through opportunity. The idea that ancient civilizations tracked celestial cycles resurfaces in these discussions, but again through a grounded lens. Historical records, while impressive, reflect long-term human engagement with the night sky. These observers relied on celestial motion to guide agriculture, architecture, and ritual. Their observations were not coordinated through external influence. They were motivated by survival and curiosity. Early astronomers sought patterns in the heavens because the sky was both predictable and essential. Modern research respects these achievements while recognizing their limitations. Ancient star charts preserved coarse patterns across generations, and while some alignments overlap with modern orbital reconstructions, these correspondences reflect the precision of long-term naked-eye observation, not advanced knowledge beyond their time. Understanding this allows scientists to appreciate the continuity of astronomical inquiry without attributing more than what evidence justifies. In this way, even history becomes part of the scientific narrative surrounding Atlas. The object serves as a bridge between past and present, linking humanity's first skywatchers with the advanced observational tools of today. It highlights the unbroken thread of curiosity that has carried human civilization from stone markers to spacecraft. And in doing so, it reframes the event not as a disruption but as a continuation of a much older conversation, one between human beings and the cosmos unfolding across millennia. As Atlas approaches perihelion, its activity may increase, jets may flare, dust may rise, spectral brightness may oscillate. These variations will be measured, modelled and debated not because they are alarming, but because they are rich with information. Every photon reflected or emitted by the object contributes to humanity's growing understanding of interstellar chemistry and dynamics. And beneath all of these analyses lies a quieter truth that the universe is generous with its details, offering them freely to anyone patient enough to observe. The cosmos operates on scales beyond comprehension, yet it expresses itself through phenomena small enough to fit within the sensitivity limits of our detectors. Atlas is neither message nor omen, it is simply part of that ongoing expression. For scientists, this is enough. For observers, it is a reminder that the universe's most profound lessons often emerge without noise or spectacle, and for humanity as a whole, it is a moment to witness something that has travelled farther than any spacecraft shaped by forces older than life itself. The object moves onward. Mars continues its cycles, Earth continues to watch, and the space between them remains a quiet expanse of dust photons and gravity, unchanged and unhurried as it has always been. As perihelion draws nearer, observational networks across Earth begin increasing their sampling frequency, the object's changing brightness, rotational modulation, and spectral variations are monitored around the clock, not out of concern but out of opportunity. Interstellar fragments rarely pass close enough for such detailed study, and the scientific community treats each dataset like a faint echo from another region of the galaxy. Data that will never repeat once Atlas drifts past and disappears into the outer dark. The closer Atlas moves toward the Sun, the more its surface responds to solar radiation. Temperature gradients rise and fall across uneven terrains. Frozen volatiles trapped within microfractures begin to sublimate at slightly different rates. Each release creates tiny transient jets, impossible to see directly but visible through the subtle perturbations they imprint on the trajectory. These deviations are small enough to escape casual notice, yet measurable through precision tracking. When the models account for these non-gravitational forces, something elegant emerges. The object's path becomes a portrait of thermodynamics rather than a puzzle of intention. Jets accelerate it fractionally. Cooling reduces acceleration. Light pressure from the Sun contributes its own continuous nudge. Together, these influences form a dynamic interplay that resembles a slow natural choreography, subtle, delicate, and entirely consistent with what previous interstellar visitors have exhibited. From Earth, the data arrive as streams of numbers, photons counted, frequencies catalogued, intensities charted. But scientists often describe an emotional undercurrent to this work. They speak of a quiet admiration for how predictable physics becomes when enough information is gathered. What initially appears uncanny soon resolves into clarity. The unknown doesn't shrink, it becomes framed by understanding, and in that framing the universe feels less mysterious and more harmonious. Mars too remains steady. Atmospheric models continue matching predictions, slight increases in regional dust density during southern spring stabilization of polar frost lines, low-intensity thermal waves spreading through the mid-latitudes. These observations confirm long-standing studies that map how sunlight and surface material interact to create the planet's unique climate cycles. Nothing here steps outside the parameters documented by decades of missions. Even the most precise spectroscopic measurements show no meaningful change in the composition of the Martian atmosphere. Trace gases fluctuate within established seasonal boundaries. CO2 cycles follow predictable pathways. The planet continues to behave as a cold, thin-aired world, responding to sunlight axial tilt and internal inertia. If Atlas contributes anything at all, it is indistinguishable from the natural cosmic background, like a single grain added to dunes that shift endlessly in the Martian wind. The broader solar environment shows its own subtle motions. The heliospheric magnetic field begins transitioning through a phase of gentle restructuring, something solar physicists have charted many times before. Small instabilities ripple outward as the solar cycle progresses. Energetic particles scatter more intensely in certain regions and less in others. These conditions influence how well radio waves travel, how auroras appear, and how planetary atmospheres respond at high altitudes. And so as the object drifts nearer to the Sun, the accumulating data do not tell a dramatic story. They tell a quiet one a story about temperature gradients, pressure differentials, dust trajectories, isotopic ratios, and orbital mechanics. They describe a fragment of another world responding to forces that permeate the galaxy, light, heat, motion, and time. In that sense, Atlas becomes less an object of intrigue and more a reminder of how interconnected cosmic processes truly are. The scientific community understands that the object will soon begin its outward journey, gradually dimming as it recedes into the heliosphere's vast envelope. When it does, the data stream will slow. Observatories will shift their attention to other targets. Mars will enter another season. Earth will continue refining its models, and the universe will remain unchanged in its quiet persistence. What will remain, however, is the knowledge gained improved orbital models, refined thermal simulations, updated spectral libraries, deeper context for interstellar chemistry, and perhaps most importantly, a renewed sense of humility. Atlas has reminded researchers that the cosmos does not always reveal itself through dramatic events. Sometimes it reveals itself through small consistencies, gentle variations, and the steady unfolding of natural law. Those who study these patterns often describe a particular stillness in the work. It is the feeling of being aligned with something vast, not because it demands attention, but because it simply exists. The object moves on a path shaped by forces older than humanity. Mars continues its timeless cycles. Earth watches with an intelligence that has only recently begun to understand how vast the cosmos truly is. In the end, the significance of this moment does not lie in Atlas itself, but in our ability to observe it with clarity, quietly, patiently, and without the need for spectacle. The universe speaks in the language of physics, and those who listen do so not for answers but for understanding. And understanding in this context is its own kind of peace. As Atlas rounds its closest point to the Sun, the last surge of activity plays out exactly as physicists predicted. The surface warms, crystalline structures fracture, and a final wave of soft sublimation releases a faint halo of dust that disperses into the solar wind. These particles drift outward, carried along magnetic streamlines like pollen released into a vast invisible current. None of it is dramatic to the eye, yet every fragment is recorded with care, logged into datasets that future researchers will comb through page by page. Once the object begins its outward arc, the measurements change subtly. Brightness stabilizes, thermal output decreases, the jets lose strength as remaining volatiles retreat into deeper layers, far from the sun's warmth. Atlas becomes quieter, as though the object itself is settling into the long cold glide that awaits beyond the orbit of Jupiter. For the first time since its discovery, its behavior resembles a return to baseline, a gentle diminishing rather than the gradual unveiling that characterized its approach. Mars, meanwhile, continues its slow transition into the next phase of its seasonal cycle. The mid-latitude temperature variations soften. Dust concentrations begin falling toward expected levels. Polar regions grow more reflective as thin frost sheets start to form again. Each change aligns with decades of collected data, reaffirming the consistency of Martian climate models. Nothing about the planet's evolution suggests disruption. Nothing breaks from its quiet script. It remains a world shaped by sunlight, geology, and time. Earth's instruments continue watching both worlds, gathering the final arcs of information before Atlas slips beyond the limits of high-resolution tracking. Observatories in chiller Hawaii, Spain, and Australia alternate their observations to keep a full 24-hour record. Space-based telescopes contribute snapshots where Earth's atmosphere cannot. Together, the instruments weave a tapestry of data like curves, radial velocities, spectroscopic lines, surface temperature signatures. When assembled, the tapestry reveals a coherent story, a natural object shaped by ancient processes moving through a solar system that responds only in accordance with established physics. Discussions begin to shift toward what comes next. Plans for future missions, perhaps one day to intercept objects like Atlas, gain new momentum. Engineers consider how improved propulsion or early detection could allow humanity to study such visitors up close. Astronomers refine algorithms that sift through sky surveys for faint, fast-moving interstellar candidates. Chemists update hypotheses about the formation of complex molecules in deep space. Every discipline takes something from this moment. None of these developments stem from urgency. They stem from the quiet expansion of curiosity. Each discovery becomes a stepping stone toward broader understanding. Atlas may fade from view soon, but the questions it raised about interstellar chemistry, planetary atmospheres, solar dynamics will continue reverberating through scientific work for years. As the object angles outward toward the dark beyond Mars, its light dims gradually. Telescopes require longer exposures to capture it. Eventually it becomes a point indistinguishable from the background starfield, a faint mote drifting toward regions where our instruments cannot follow. It will continue on its journey long after humanity has shifted its focus elsewhere, carrying a record of the places it has passed through, etched invisibly into its structure. In some quiet way, there is comfort in knowing that it will keep going. It has no destination, but it moves with certainty. It has no mission, but it follows a path shaped by forces older than language. It will traverse the heliosphere, cross the bow shock, where the solar wind yields to the interstellar medium, and re-enter the galactic currents that shaped it long before our sun existed. Its story continues unobserved, yet unbroken. For the scientists who followed its progress, the final observations are tinged with a sense of completion. The data have been gathered, the models have been updated, the object has taught all it can during this brief intersection of trajectories. What remains is reflection on how far human knowledge has come, on how quietly the universe shares itself, and on how much remains to be learned from objects that wander across the boundaries of stars. As Atlas fades, Mars continues its slow rotation under a pale sun. Earth turns beneath the weight of its own atmosphere, carrying observatories that will soon focus on new questions. And overhead, the night sky stretches on an expanse of scattered photons drifting dust in distant orbits, moving with a patience that surpasses every generation that attempts to understand it. The story does not end. It simply dissolves into the larger rhythm of the cosmos. In that rhythm there is no urgency, no revelations, no hidden design, only the vast ongoing interplay of matter and motion. And those who study these motions find a simple truth, reflected back at them, that understanding does not diminish wonder, and that the quiet acceptance of what is can be more profound than any search for what might be. The universe continues in silence, and we for a moment had the privilege of listening. Traveller, we have reached the edge of tonight's journey, from the quiet deserts of Mars to the drifting shadow of Three-Eye Atlas. We have followed a thread of mystery that stretches far beyond our small blue world. And now, as the dust settles and the echoes fade, we're reminded of something simple, something profound the universe never stops whispering. It only waits for someone patient enough to listen. What Three-Eye Atlas is doing to Mars may remain uncertain for years, perhaps lifetimes. But the act of observing, of turning our attention toward the dark and asking gentle questions, that is what shapes us. That is what connects us to everything that drifts, glows, or lingers in the cosmic deep. You, observer, have walked through a corridor of possibilities tonight, and whether answers come or stay hidden, the wonder itself is real, and it belongs to you. As you settle into sleep, remember this. We are small, yes, but never insignificant. Each thought you carry is its own universe. Each breath a quiet orbit. And somewhere out there beyond the cold silence, something ancient still moves, steady, patient, unhurried, reminding us that mystery is not a threat but a companion. If this story found you tonight, you may stay for the next. Rest well, traveller. Stay curious. The universe will keep watch.